Once you've got the formulation, the next thing is you have to be able to jet it. So it needs to be thin enough to be jetted for the correct layer thickness and the droplet size. You then need a sufficient UV dose for the final cure, which is measured in joules, with sufficient irradiance. So dose is not the whole story. You actually need a certain power level to be able to make the process work at all. The next thing you need is the UV of the right wavelengths. And generally it's true that longer wavelengths are associated with through cure. So that's adhesion between the substrate and the ink or the coating. Surface cure is really associated with a shorter wavelength, so that's UVB and UVC, which you're not going to get from LEDs, not for the foreseeable future anyway. Also at the optimum temperature, and it's true that heat may increase the reaction rate, but there's a little problem, and that is that oxygen inhibition or oxygen quenching is actually going to be increased at increased temperatures, which again inhibits the cross-linking effects. And of course, the print substrate may actually be heat sensitive. So you probably don't want too much heat anyway, and so cold UV, as it's sometimes known, is desirable. And that substrate is going to have a range of wettability. Now, Mark Bale from Sun is going to be talking much more about things that can be done in terms of wettability in the next talk. So, photoinitiators are pretty key, and the actual selection criteria of the photoinitiators, you want, as I say, you want to have the maximum spectral overlap with the lamp emission, so what's coming out of the UV lamp, you want to be absorbed by the photoinitiator in order to create the chemical energy in the process for it to work at all. And you want minimum overlap with the absorption of the pigment all the time. And you want pretty good reactivity, so because you want to have efficient curing taking place at relatively low concentrations of photoinitiator, and you want to not have to have too massive a dose of UV to be practical. Also, the photoinitiator, it's obviously got to be readily soluble in the formulation, and it's not going to interact with other parts of the formulation. You don't want yellowing, so you don't want the actual colour of the desired colour to be affected by the photoinitiator itself. You want low odour, particularly for packaging applications, and you want low or no migration of the photoinitiator, again for packaging applications. And you want it to be easy to use, easy formulation, and you want good handling properties. So it's actually quite a tall order for the formulators. I'm not a chemist, I'm not a formulator, but I can see that there's a lot of challenges there that really the chemists are faced with to make a good UV ink. So, as I mentioned, there's relatively limited choices that you've got in terms of what you can use for curing. I'm going to list them here, and you've got, for example, xenon lamps or xenon lamps. They are generally used for flash curing, which is perhaps not so appropriate in a continuous process. The vast majority of lamps are based on mercury, so this is really probably 99% of UV cured processes right now contain a mercury lamp. Now it's either that mercury is a plasma, so it's excited either using an electric arc or using a microwave source, and that lamp is either going to have additives within it, or it's going to be a straightforward mercury vapour. Talk a little bit more about that. LEDs. a lot of talk about LEDs. They are seen as the future, very much in the industry, but they're not without their problems. What else? Not a lot, really. There's not many other things commercially available outside laboratories for providing UV sources. So you're really going to be picking one of those as a UV source. So let's look at those choices in a little more detail. This is basically what you're going to get out of a mercury plasma lamp. You're going to get a range of specific wavelengths, and those are predictable and will always occur at more or less the same, well, at the same wavelength. There's a variety of forms of lamp. There's short arc lamps like this. There's mercury xenon lamp where you've got a mixture that somewhat extends the spectrum and flattens it out a bit more. You have xenon on its own, which gives you this continuum here, but you've got sort of peaks further up. You've got also the variety of pressures that you can use in the mercury lamp, and also you've got a choice of additives. Various metal halides can be added. That's iron, which you can see extends the spectrum somewhat from its basic line spectra. You get a more broadening of the spectrum. And that one is gallium. So the choices really within a mercury lamp are largely to do with having a range of peaks, particularly the 365 nanometer. That's almost always going to be a given. That a peak appears in pretty much all of these spectra. And that's where a lot of formulations really have centered themselves traditionally. As I mentioned, longer wavelengths tend to be associated with through cure, shorter wavelengths with surface curing. And that's what this lockdown here is doing, is generating UVC, which overcomes oxygen inhibition at the surface. So then the choices that are open to you once you've accepted that mercury is the predominant form of UV source are really what additives you're going to have in there along with the mercury and what pressure it's going to be operating at. To compare that to LEDs, let's just recall that we've got a photoinitiator, often photoinitiator with a peak absorption. Certainly not very obvious on this scale, but if you sort of zoom in, you will see these peaks occurring from these two, like TPO. You'll see these absorption peaks that are occurring quite conveniently around this 365 nanometer. And this spectrum here, the blue one, is the lighter line and the darker line here. These are from one of our standard on-the-cure mercury spot curing systems. And to compare that to LEDs, we've got a couple of peaks here, 365 nanometer LED and the 400 nanometer LEDs that we have within our choice of system for pinning that I'm going to talk about. And you can see that, and this is illustration only, but basically there's a lot of energy, power concentrated into quite a narrow wave band, typically 10 nanometers wide, around these peaks. So you've got a fairly strong mercury line at 405 nanometers that you would always have. You've got generally an even stronger line at 365. So these two mercury peaks really are mimicked by these LED sources.